Hey guys, welcome to the Biomechanics 1 video series. We are continuing with our third and most likely final video on this impulse-momentum relationship. What we've realized so far is that there's a significant relationship between the impulse-momentum equation. We've spoken about where it's derived from, we've uncovered individually what momentum entails and what impulse entails, and now we're working through a couple of worked examples where we're putting the two together. So just a quick refresher, we said that the force acting on an object multiplied by the time over which that force tends to act causes some kind of change in momentum, right? We spoke about the fact that both impulse and momentum are vectors, therefore their direction is obviously going to be really important, and we have to factor that in to our analysis. Remember, anything acting up and to the right will typically take as positive. That's what I'll be doing in this video in any case. So how you set it up is completely up to you, as long as you are consistent, right? So I have a scenario here where I have a baseball bat and I have a ball traveling to the left at 38 meters per second. The ball makes contact with the bat for a period of time, and we'll say that this time of contact is going to be equal to a very short period of time, 0.016 seconds, right? The ball then changes direction with a different speed of 58 meters per second to the right. So our goal is to find out what was the force of impact between the bat and the ball during its time of contact. Okay, so we'll have to set up this equation in a manner that we can factor or solve for this force. It's not going to give us what the peak is, and that's something that we discussed under the video unpacking impulse. At best we'll get an average, okay, since most of these values that we're dealing with will be average values. It's very difficult to determine the instantaneous value and therefore the peak value, but it's a good approximation nonetheless. Okay, so what do we have here first? Let's look at the momentum of the system in this first instance. So we are looking at the mass of the ball. Oh, that's something else that I have to put in. So the mass of the ball is 0.14 kilogram. Mass is equal to 0.14 kilograms. Okay, so what we'll set up is what is the change momentum of the entire system. So change in momentum is something that we discussed in quite a bit of detail. It's this delta P, right, which is equal to the final momentum minus the initial momentum. Okay, so the final momentum of this particular system, remember, it's immediately before impact and during impact and immediately after impact between the ball and the bat. The reason that we are calculating the impact by the bat on the ball is, if you remember, that the situation here comes from Newton's second law, which states that force acting on some object is equal to the mass and acceleration of the object. So it is by something on something else, and this change in something else is something that we can measure. And since we're measuring this change in velocity of the ball, we are calculating the force of impact by the bat on the ball in order to cause that change in momentum. Okay, so the final momentum immediately after impact of this ball is going to be the mass of the ball times the final velocity of the ball minus the mass of the ball multiplied by the initial velocity. Okay, so the mass of the ball is 0.14 kilograms. The velocity of the ball was 58 meters per second to the right, minus mass of the ball is unchanged, 0.14, multiplied by, and this is where the direction really becomes important. Remember that this ball was moving to the left. We can therefore ascribe a negative to it. So don't forget to do that. So negative 38 meters per second And when I multiply this out, I should get 13.44. 13.44. Don't forget your units, kilogram meters per second. Okay. The next thing that we know is that the impulse generated is equal to the change in momentum. Okay, well, we've just calculated this change momentum over here, so we can say that the impulse is equal to the force times the change in time, or the time over which that force acts, which is going to be equal to that 13.44 that we've just calculated, kilogram meters per second. So our goal is then to isolate the force, so I can take this time and divide it out. So force is equal to 13.44 divided by this change in time, which we said was 0.0016 seconds. And I'm left with an impact force of 8,400 newtons. 8,400, and our units there are newtons. So a very, very large force in order to cause this change in momentum that we saw here, right? So 8,400 newtons is close to 800 kilograms of force during the time of impact. It's one of the reasons why you see that ball deform so much during those impact situations. Okay. In a second example, we look at a collision of a car. So impact forces of car against a wall. So again, this would require quite high speed cameras. We've got the mass of the car, it's about 1.5 tons, and it undergoes a collision in 0.15 seconds. So it has an initial velocity. I've already put the sign in, left is negative. So initial velocity of 15 meters per second. As it then collides with this wall, it crumples and actually ricochets somewhat, that its velocity immediately after impact is 2.6 meters per second to the right. So again, the question comes, what is the force of impact? Right? Really important. So similar setup to the previous question, we'll start off by finding what the change in momentum is, which is mass times final velocity minus mass times initial velocity. Again, we're assuming that in this case mass is considered to stay consistent. So we'll take this 1,500 multiplied by the final velocity, which was 2.6 meters per second, minus this 1,500 times this negative 15 meters per second. Okay, that should give me a change in momentum. Let me just double check. Of 1,500 times 2.6, which is just doing the step by step to make sure that there's no mistakes in these calculations. This gives me 3,900 minus, or in this case it will actually become plus, because a minus times a minus is a plus. 1,500 times this 15, 22,500. 22,500. So that should give me a total of 22,500 plus 3,900, 26,400, 26,400 kilogram meters per second. Okay, so what would be the force of impact? So we know already from the previous question that the impulse is equal to the force times this change in time, which has to then equal this 26,400. So the force of impact is going to be equal to 26,400 divided by 0.15, which is the time of the collision, and that gives me 176,000 newtons of force, which is again very, very large. So if you look at this scenario, if I just had to rewrite this equation, to basically state that the force of impact is equal to the change in momentum over this change in time, right? So how can I decrease this force? So I can either decrease the momentum. So the way in which I can do that is maybe change the material of the car to maybe increase this ricochet velocity. So if I increase this, you'll realize that this impact situation will be significantly less. Obviously decrease this initial velocity over here would ultimately decrease the momentum. I could also increase the time over which this force tends to act, right? So you'll find that force of impact will decrease if momentum decreases or if time of collision increases, right? So those are really, really important factors here. So in most cases, what they'll do is they'll increase this impact time to decrease the force of impact. One of the reasons that we have airbags in the car, right? Okay. One last question, a slightly more difficult one. I have an 82 kilogram person, right? In this case, what I'm trying to calculate is the force of landing. So what I have here is I have an 82 kilogram person that steps off a 70 centimeter wall. Upon landing, they tend to bend their knees so as to stop the downward motion, and the time of the collision is 0.28 seconds. So what's the force of impact by the ground on the person? Okay, so really important setup in this scenario is the fact that I have this person ultimately jumping down, and on landing they bend the knees to increase this time of impact. So how do I go about solving this situation? It requires more than just the impulse momentum, for reasons that we'll discuss just now. If you think about it this way, I have an impact situation when this person is ultimately landing. So if they're trying to bend their knees as they land, so it looks like this guy's broken his leg, but he's just trying to bend his knees. So I have an impact situation between the person, right, and the ground that they're ultimately landing on. Right, so they're trying to slow themselves down as they're doing it. Okay, so this person must have some kind of initial velocity on the way down, right? Then their final velocity is ultimately where they reach a stop. So that should be 0 meters per second in this particular scenario. This is now isolating this portion here where this person has already landed. So that's kind of what we're just projecting on here. So in this particular scenario, this is where our collision tends to happen. Right, he has some initial velocity as he's landing. He then stops. It's unlike the car or the ball example, he wouldn't ricochet back. He's going to stop downwards. The time of this impact, right, this delta t, we said is 0.28 seconds. Okay, so the key here is to find out what was his initial velocity on landing, right? So we kind of have to work backwards and say, well, he stepped off a wall and the height of that wall is 70 centimeters, right? So between here and here, as soon as he steps off, we're dealing with some kind of projectile motion. He's in the air, he's airborne, and therefore will have some velocity as he starts to come down. So if I unpack this a little bit more, he'll have again some initial velocity here, which is equal to 0 meters per second, and we'll call this part 1 and this part 2 over here. So in part 1, his final velocity is what we're ultimately trying to find. His acceleration is just gravity, which is equal to negative 9.81 meters per second squared. We don't have time. Remember, the time that we have here is the time of the collision, not the time it takes him to fall from the wall down to the ground. And we have some change in the vertical displacement, which was this 70 centimeters or 0.7 meters. So we have a couple of equations that we could possibly use. Easiest one, remember we're trying to solve for final velocity, right? So if you look at your uniformly accelerated motion, you'll find this one, final velocity squared is equal to initial velocity squared plus 2as. Okay, remember you'll have to plug in all your vertical values. So if I would substitute these values in, my initial velocity was 0. Final velocity squared, that means final velocity is going to be equal to the square root of 2 times a times s. Okay. Since I'm moving downwards, s is also going to be negative 0.7. Remember that delta s is equal to s final minus s initial, or displacement final minus displacement initial. So my final position is on the ground, which I'll call 0, and my initial was this 0.7, right? So that's going to equal negative 0.7. So when I plug values in, what I'll get is the following: 2 times negative 9.81 as my A, and negative 0.7 as my displacement. So a negative times a negative gives me a positive, and I will get that my final velocity is a value of 3.7897 meters per second. Okay, so I'm going to keep that in mind as I deal with part 2. Part 2 is where I'm trying to solve for this force of impact, right? So I use my impulse momentum calculations is equal to, let me just undo that, do this change in momentum. Okay, so force of impact is going to be equal to my change in momentum over my change in time. So if I just had to unravel this a little bit more, it's mvf minus mvi over delta t. Now I just plug in my values. So the mass of this individual is 82 kilograms, right? 82 kilograms. And then here, now my final velocity is 0 as I bring my body to a stop, minus this 82 times what my initial velocity was coming into this collision, which was what I just calculated. Let me just change the color to make it consistent. This 3.7897, and then I divide all of that by the time it took me to come to a stop, which was, we said 0.28 seconds. And that will give me an impact force of 82 times 3.7897 divided by 0.28, and it's 1,000, let me just find out where my cursor is, whatever, 1,109.8 newtons. Okay, which is equal to 1.38 times body weight. Again, let me just find where this cursor is, which is equal to 1.38 times my body weight, which is quite a, it's not a huge force of impact, but it is quite a significant amount. How did I get this 1.38 times body weight? I'll just show you here. So what I would do is 1,109.8, and I divide it by my mass times the gravitational acceleration, which is my weight, and I'll get 1.38. Okay, so the force of impact is 1.38 times how much I weigh in terms of mass. Okay, which is what I plugged in here. Okay, so a little bit more tricky, but very interesting nonetheless. So just me landing from a height of 0.76 meters has an impact force of 1.38 times body weight. Quite substantial. Very cool. Alright, thanks for listening.